Hello, we are continuing Chapter 8 on multiplication, and today we will cover multiplication properties. There are 6 properties that we'll cover. So to begin, let's just assume that A, B, and C represent natural numbers. So remember, natural numbers are things like 0, 1, 2, 3, 4, and so on. Sometimes they're also called the whole numbers. The first property I want to talk about is the closure property. Closure says if I take two natural numbers, say A and B, and I multiply them together, the result will also be a natural number. This is kind of obvious, right? 3 times 7, 3 is a natural number, 7 is a natural number, their product 21. Yes, 21 is a natural number also. But even in cases where we don't know the answer, 192 times 74. So I don't know what that answer is off the top of my head, but whatever it is, I am assured that the answer is a natural number. I can extend this idea of closure to sets. How about the set containing all even natural numbers? 2, 4, 6, 8, 10, and so on, forever and ever. Is this set closed under multiplication? It is, because if I multiply any two of these even numbers together, I will get another even number. So closed, yes. How about the set of all odd numbers? 1, 3, 5, 7, 9, and so on, forever and ever and ever. Is this closed? And if you think about it for a minute or two, yes, it is. If I take any two odd numbers and multiply them together, I will get another odd number. So the set of odd numbers is closed under multiplication. We had seen the set like this earlier when we were talking about addition. The set of odd numbers is not closed under addition, because if I add two odd numbers, I'll end up with an even number. But in multiplication, it is closed under multiplication. How about something like 3, and then I'll double 3. 3, 6, 12, 24, 48, forever and ever and ever. Is that set closed under multiplication? No, it's not. So something like 3 times 6 is 18, but 18 is not in the set. Or even 3 times 3. 3 times 3 is 9, and 9 is not in the set. All right, so that's closure. The natural numbers are closed under multiplication. The commutative property. This says if I have two numbers, A, B, and I multiply A times B, the result is the same as if I had multiplied B times A. So 7 times 3 is the same as 3 times 7. Not much more to say about this, but just watch out for that word, commutative. It's like commuting, so moving around, and there's no N in that word. Okay, moving on. Number 3, the associative property. Here's where I need 3 or more letters. If I compute A times B times C, well, in order to do multiplication, I need to do pairs of numbers that are multiplying. So I have a couple choices. I can either multiply A and B first, get that result, and multiply times C, or I could multiply B and C first, get that result, and multiply times A. And the associative property says it doesn't matter how I group these things or associate them, I'll get the same answer. So 7 times 2 times 3, if I group the first two together, I get 14 times 3, and 14 times 3 looks like 42. Or if I try 7 times 2 times 3, I get 7 times 6, and 7 times 6 is 42. It doesn't matter how I group them. One thing to note with associative is that the order stays the same. I have A, B, C in that order. A, B, C. In my number example, I had 7, 2, 3. 7, 2, 3. The order stayed the same. It was only the grouping that changed. The associative property says it doesn't matter how I group things. The answer will be the same. It's the commutative property where I start moving things around. Okay, moving on to number 4. The identity property. The identity property says there is a very special number with multiplication. It is the number 1, and 1 has the property that 1 times A equals a for any number a that I choose. One is called the multiplicative identity. We saw an identity with addition also. Do you remember? There is an additive identity. And so, just by the way, to recall, 0 is the additive identity. And 0 has the property that 0 plus a equals a for any a. So there is a multiplicative identity, 1, and there is an additive identity, 0. But in multiplication, 0 plays a special role. So here is the 0 property in multiplication. 0 times a equals 0 for any a. And actually, we don't have any number like this in addition. You can check it for yourself. But 0 has this property. 0 times anything is 0. Our last property in multiplication is the distributive property, and this is the one that ties together the multiplication and addition. How do they interact together? So the distributive property says a product, a times this sum, b plus c, can be computed as a times b plus a times c. We think of distributing the a over the b plus c. We sometimes say that multiplication distributes across addition. Multiplication distributes across addition. So if I have 2 times 7 plus 1, I could figure this out as 2 times 8, which is 16. Or I could use the distributive property, and this is 2 times 7 plus 2 times 1, which just gives me 14 plus 2 and 16. So I end up with the same answer. I can distribute multiplication across addition. Let's look at a few small problems, 3 small problems that use the multiplication properties. Number 1, use the area model to justify the distributive property. Why should the distributive property even be true? Here's one way we can think about it. So let's recall the distributive property says that a times b plus c is ab plus ac. So let's make a rectangle here, and I'll divide my rectangle into 2 sections. And let's suppose one length on top is b, the other length on top is c, and the height of the rectangle is a. Well, the area model says that the area of a rectangle is height times width. So the area of the rectangle on the left is simply AB. The area of the rectangle on the right is A times C. But look at this. What about the area of the overall big rectangle? What is the area of the big rectangle? So that has side length B plus C. So the overall area is A times B plus C. That big area of the rectangle is equal to the smaller area on the left plus the smaller area on the right. And there, the area model of multiplication is a nice justification for the distributive property. Number 2, use the joining equal lengths model to justify the commutative property. So remember, joining equal lengths says that I can think of multiplication as joining several segments of equal length. Let's maybe show 2 times 3 is the same thing as 3 times 2. So 2 times 3, let's imagine I have some kind of a stick of length 3. Imagine dividing this into roughly 3 equal parts. So a stick of length 3, and I put together end to end with another stick of that same length. Another stick of length 3, so I have 2 times 3. But underneath that, perhaps I place a stick of length 2, and then a second stick of length 2, and a third stick of length 2. Length 2, length 2, length 2. So on top, this looks like 2 times 3. On the bottom, it looks like 3 times 2. And what's important is that if I physically do this, if I take these blocks and I lay them end to end, we notice that the ends line up on the left, the ends line up on the right, and that's how I know that these two guys are equal. They have the same length. So 2 times 3 is the same thing as 3 times 2, as justified with this joining equal lengths model. One last problem. What property of multiplication allows us to assert that 16 times 5 equals 8 times 10? We'll see problems like this a little bit later on with mental math, because do you know what the answer to 16 times 5 is? That's a little harder, but 8 times 10 is pretty easy because we have a multiplication of 10 in there. So have you decided what property is this? 16 times 5. Here's what I'm going to do. I'm going to break up that 16. That 16 is really 8 times 2 times 5. And now I can reassociate the parentheses. That's 8 times 2 times 5, which is 8 times 10. So 16 times 5 equals 8 times 10, and the key step was in the regrouping. So that was the associative property. That's what allows me to make this kind of simplification. Alright, so we've talked about the different multiplication properties and see how they relate to some of the models and some of the questions that we can ask. Give the worksheet problems a try. There isn't really a homework section in 8b, but there's a really interesting historical note. Don't just cast it aside. Read the historical note. This distributive property and this area model, they go back thousands of years, and it's interesting to see how the ancients were thinking about these same things that we're talking about today. So take a look at that and appreciate some ancient Euclidean history. Okay, get to it and ask if you have questions.